Hello everyone, I'm Norman Wildberger. In this famous math problem, we are going to be looking at a very interesting family of elementary polynomials called cyclotomic polynomials. And the problem is how to calculate the cyclotomic polynomials, which we'll call phi sub n, for n a natural number. These cyclotomic polynomials arose first probably in the context of number theory with the work of Carl Friedrich Gauss and regular polygons. They're naturally connected with complex numbers and the algebra of roots of unity. There's natural connections with Fermat's last theorem, and the polynomials are closely connected with important extension fields of the rationals called cyclotomic fields. Now, these topics are quite close to a general area of mathematics called algebraic number theory, and an associated kind of branch of algebra called Galois theory, which is concerned with fields more generally and symmetries of fields associated ultimately to solutions of polynomial equations. So these polynomials, although they're quite modest and elementary, they do have a lot of interesting connections with interesting things. Let's start out by looking at the analogy between number theory and polynumber theory. So polynumbers are my preferred way of thinking about polynomials. So instead of having polynomials in a variable x, I prefer to frame things in terms of polynumbers in alpha, and alpha turns out to be just a particular polynumber. So I basically have a data theoretic point of view towards this, and I will give you some references to that if you're interested, but it's not really crucial, but I do just prefer to use the language of polynumbers. So there's an analogy between questions of number theory and questions of polynumber theory. Okay, so with number theory, we might be working with the natural numbers, like 5, or maybe with integers, like -7, or perhaps with rational numbers, like 4/9. Correspondingly, in the world of polynumbers or polynomials, we have polynet, which refers to polynumbers with natural number coefficients, like 1 plus 3 alpha. Or we might have polyint, where we allow integer coefficients, like 2 minus alpha to the 5th. Or we might have polyrat, which are quotients of integral polynumbers, like 1 plus alpha to the 7 over 4 minus alpha cubed. So there's a correspondence here. This is a somewhat more sophisticated version of number theory, where we expand our consideration to not just numbers, but numbers augmented with these more general things called polynumbers. Now, in ordinary number theory, the prime numbers, 2, 3, 5, 7, etc., play a very major role. And correspondingly, in polynumber theory, the irreducible polynumbers are sort of corresponding. For example, 1 plus alpha squared. That polynumber cannot be expressed as a product of polynumbers of lesser degree. It's irreducible. So, for example, one of the important applications of prime numbers is unique factorization. That if you have some number, say like 2 to the 11th minus 1, that can be factored into a product of prime factors. In this case, 23 times 89. Well, correspondingly, in the polynumber world, if you have some polynomial or polynumber, say 1 minus alpha to the 9, then that has a factorization into irreducibles, which is also unique in the same way, unique up to just moving the factors around. In this case, it factors as 1 minus alpha times 1 plus alpha squared times 1 plus alpha cubed plus alpha to the 6. So there's a kind of a correspondence here, and that's going to be an important part of this story. We are going to be exploring aspects of factorization in this story here, but there's close connections with factorizations in the more ordinary number theory. So before we start talking about factorization with polynumbers, let's just have a little bit of a look at Mersenne primes, or the search for Mersenne primes. Mersenne primes are particular primes which have the property that they're of the form 2 to the something minus 1. For example, 2 to the 13 minus 1 is 8,191. That happens to be a prime. So that's called a Mersenne prime. So here's a list of numbers of the form 2 to the n minus 1. 2 to the 1 minus 1 is 1, 2 squared minus 1 is 3, 2 cubed minus 1 is 7, 2 to the 4th minus 1 is 15, which is 3 times 5. 2 to the 5th minus 1 is 31. So far we have 3 primes. Then 2 to the 6th minus 1 is 3 squared times 7. 2 to the 7 minus 1 is 127, that's prime. 2 to the 8 minus 1 is 3 times 5 times 17. 2 to the 9 minus 1 is 7 times 73. 2 to the 10 minus 1 is 3 times 11 times 31. 2 to the 11 minus 1, we've seen this one already, that's 23 times 89. 2 to the 12 minus 1 is 3 squared times 5 times 7 times 13. 2 to the 13 minus 1 is 8,191, which is prime. 2 to the 14 minus 1 is 3 times 43 times 127. And we could carry on like this, and it's somewhat interesting. Okay? If a little bit irregular, but nevertheless, if we look at this for a while, we see that there are some kinds of patterns that we can observe. For example, 2 to the 14 minus 1. The 14 is equal to 2 times 7. 2 times 7. Now, when we did 2 squared minus 1, we got 3. When we did 2 to the 7 minus 1, we got 127. And we see that both 3 and 127 are factors of 2 to the 14 minus 1. So there's certainly some connection between these things. And here is a very important fact in this context, that if you're looking for a Mersenne prime of the form 2 to the n minus 1, then we require, in order for that to happen, that n is prime. So if n is not prime, like here, there's no way we're going to get a prime. So here, for example, 13 is prime, we get a Mersenne prime. When we have 7, we get a Mersenne prime, 5, 3, and 2. But note, the converse is importantly not the case. So just because n is prime does not mean that 2 to the n minus 1 is prime. For example, 2 to the 11 minus 1 is not prime. But everything that we know about primes suggests that there's no kind of easy way of cooking up primes by this kind of reverse converse inclusion. We can't just cook up primes easily by, imposing some condition on some exponent or something. Because after all, the total number of primes that are known is limited. We have a largest prime, which is no doubt a Mersenne prime these days, and it's hard to get bigger primes. So this is a good preliminary to thinking about cyclotomic polynomials or polynumbers. Okay, so now let's move to the polynumber land, and we're going to consider factoring polynumbers of the form 1 minus alpha to the n, where n is a natural number. So we're restricting ourselves to a rather specific family of polynumbers and thinking about their factorizations. So what we get is quite interesting, and so let's have a look at it. So these things here are going to be playing some important role. So first of all, 1 minus alpha to the 1 is just 1 minus alpha. 1 minus alpha squared is the difference of squares, so it factors as 1 minus alpha times 1 plus alpha. 1 minus alpha cubed has a factor of 1 minus alpha. In fact, all of these will have a factor of 1 minus alpha because alpha equals 1 is a 0 of this polynumber, so 1 minus alpha is always a factor. The other factor is 1 plus alpha squared. Here we have 1 minus alpha to the 4th. That's 1 minus alpha times 1 plus alpha, same thing we got up here, times an additional factor, 1 plus alpha squared. When we get to 1 minus alpha to the 5th, something a little bit interesting happens. We get our standard factor together with this one, 1 plus alpha squared plus alpha cubed plus alpha to the 4th. With 1 minus alpha to the 6th, we have our standard one and 1 plus alpha. Then we also have 1 plus alpha squared, which happened here, and 1 minus alpha plus alpha squared. 1 minus alpha to the 7, we get something like we did for 5, the standard factor, and then the sum of all the powers from 1 up to alpha to the 6th. 1 minus alpha to the 8 is 1 minus alpha, 1 plus alpha squared, 1 plus alpha to the 4th. So there's some kinds of patterns here, but it's certainly not obvious how to carry on in general. So let's have a look at some more because they are important for this discussion. 1 minus alpha to the 9 is 1 minus alpha times 1 plus alpha squared times 1 plus alpha cubed plus alpha to the 6. 1 minus alpha to the 10 is a lot like 1 minus alpha to the 5th, this factor and this factor, but there's also 1 plus alpha, and then there's this factor here which is a lot like this one, except with minus signs and plus signs alternating. 1 minus alpha to the 11, well, that's similar to what we've seen before, the 1 minus alpha factor, and then this sum of all the powers up to alpha to the 10. 1 minus alpha, 12. 1 minus alpha, 1 plus alpha. 1 plus alpha squared. 1 plus alpha squared. 1 minus alpha plus alpha squared. And 1 minus alpha squared plus alpha to the 4th. 1 minus alpha to the 13, that's somewhat predictable. 1 minus alpha to the 14, something like this, with this term here and this term here being very close, except here the coefficients are alternating. 1 minus alpha to the 15 is 1 minus alpha times 1 plus alpha squared times this one here, that's associated sort of to the 1 minus alpha to the 5th. And then this new one, which is a little bit odd, 1 minus alpha plus alpha cubed minus alpha to the 4th plus alpha to the 5th minus alpha to the 7th plus alpha to the 8th. And then with 1 minus alpha to the 16, we get something that's somewhat more predictable. 1 minus alpha, 1 plus alpha squared, 1 plus alpha to the 4th, 1 plus alpha to the 8th. So maybe your appetite here is whetted a little bit and you're kind of interested. I wonder how this carries on. Could I predict what happens, say, for the next 10 or 20 factorizations? That's an interesting kind of challenge. And how do we actually come up with these factorizations? It's easy enough for a modern computer program. They're very good at factoring polynomials or polynumbers, so a computer will spill these things out instantly. But still, how do we calculate these things by hand? And what's actually going on here? Well, hidden in here, maybe not so hidden, are these interesting cyclotomic polynumbers or polynomials. So now we come to two important theorems. The first theorem allows us to bring out these cyclotomic polynomials and sort of identify them. And then the second one tells us exactly what the factorization of these polynumbers 1 minus alpha to the n is in terms of these cyclotomic polynomials. So the first one we'll call the cyclotomic polynumber theorem. And we'll state it like this. For any natural number n, which is bigger than 0, so starting with 1, there is exactly one irreducible factor phi sub n of 1 minus alpha to the n, which is not a factor of any 1 minus alpha to the k, where k is some number less than n dividing n. So when we get to n, of all those factors that 1 minus alpha to the n might have, there's exactly one which we haven't seen before. And that's going to be what we define to be the nth cyclotomic polynumber, phi sub n. And then the cyclotomic factor formula is that, again, for a natural number n, 1 minus alpha to the n is the product. So this big pi means product. A product over all the natural numbers d which divide n. So there's the product over d, where d divides n, of phi sub d. This is telling us how this polynumber factors into actually irreducibles. So it turns out that this thing is irreducible. We're not claiming that yet, but that's actually what happens. So I want to illustrate these two things by going back to our lists and sort of seeing where the cyclotomic polynumbers appear. Okay, so let's have a look at the cyclotomic polynumbers, starting with n equals 1. So this first thing that we get, the 1 minus alpha, that's going to be phi sub 1, okay? And then over here with n equals 2, when we factor 1 minus alpha squared, we get one factor which we haven't gotten before, namely 1 plus alpha. So that's going to be phi sub 2. So that one there. 1 minus alpha cubed, we've already gotten that factor. So this is going to be the new one. That's phi sub 3 right there. With 1 minus alpha to the 4, we've gotten 1 minus alpha, of course, already. We've gotten 1 plus alpha. That was phi sub 2. 2 divides 4. So this one here, this last one, I should have underlined that one also. This one here is going to be phi sub 4. With n equals 5, well, obviously this thing here is going to be phi sub 5. And with n equals 6, this one we've already seen, that's phi sub 3. That one we've already seen, that's phi sub 2. This one we've already seen, that's phi sub 1. And this one here is phi sub 6. So let's just pause here and note that this thing here is indeed the product of phi sub 1 times phi sub 2 times phi sub 3 times phi sub 6. So we're running through all the divisors of 6, 1, 2, 3, and 6, and taking the product of the cyclotomic polynumbers for each one of those divisors. With n equals 7, well, we get this big thing here. That is phi sub 7. And with phi sub 8, this is the new one. So that's phi sub 8. And let's just check that this then is the product of phi sub 1, phi sub 2, phi sub 4, and phi sub 8. So let's carry on. With n equals 9, this is the new one. So this is going to be phi sub 9. With n equals 10, well, we've seen this one. This was phi sub 5. This is the new one. That's phi sub 10 right there. Okay, this one here is phi sub 11. Okay, maybe I'll squeeze it over here, phi sub 11. And phi sub 12, the one that we haven't gotten before, is this one. This was phi sub 6. This was phi sub 4. This was phi sub 3. This was phi sub 2. This was phi sub 1. So they're all arranged in terms of the divisors. This one, this last one is phi sub 12 right there. Okay, phi sub 13, well, that's just that sum, that big sum of all the powers of alpha from 1 up to alpha to the 12. So there's phi sub 13. Phi sub 14, there's the new one right there. Phi sub 15, there's the new one there. That's phi sub 15. And phi sub 16, the new one, 1 plus alpha to the 8. There it is there. So you can check that in all cases, say for example here, this power, or 1 minus this power, alpha to the 16, is the product of phi sub 1, phi sub 2, phi sub 4, phi sub 8, and phi sub 16. It's not too hard to guess what phi sub 32 is likely to be, and phi sub 64, and so on. But if we carry on for higher powers of n, some of them are maybe reasonably easy to guess. For example, 1 minus alpha to the 17, you're not going to have a hard time guessing what phi sub 17 is. But phi sub 18 might be a little bit less obvious. Phi sub 20, let's say we go down to phi sub 349. How are you going to calculate that? Well, if that's a prime, that's one thing. But if it's not a prime, then this might be quite a little bit tricky to calculate these things. Okay, so, but you can see that the way we set things up here is that it's all just really high school algebra. We're talking about polynomials or polynumbers and their factors, and we're looking at especially simple kinds of polynumbers which are quite analogous to the 2 to the n minus 1 expressions involved in Mersenne primes. So this is pretty close to that number theoretic investigation, but it's now at the level of polynomials and polynumbers, and we've identified this interesting family of new irreducible polynumbers, these cyclotomic polynumbers. However, of course, we've just stated these theorems. We have no idea at this stage how we might actually prove them. Now, if you've been following those examples that I've been looking at, there will be one case that you're probably pretty confident about. And that's the case when the exponent, say p, is a prime. Okay, and here's the proposition that encodes that if p is a prime, then phi sub p is the sum 1 plus alpha squared all the way up to alpha to the p minus 1. Okay, how do we prove that? Well, first of all, this factorization is pretty clear. 1 minus alpha to the p equals 1 minus alpha times this factor, 1 plus alpha squared all the way up to alpha to the p minus 1. In fact, this factorization doesn't depend on p being a prime. This works for any natural number n. It's really another way of writing the formula for a geometric series. This is a geometric series, and if you divide by 1 minus alpha, then you get the familiar formula for the geometric series. But what happens in the case when the exponent is prime is that this factor here is actually irreducible. It does not factor into a product of lower degree polynomials or polynumbers. And how do we know that? Well, it turns out that this thing is irreducible by a reasonably sophisticated test called Eisenstein's criterion. Now, the history of this particular result really probably goes back to Gauss, okay, in his landmark book Disquisitiones Arithmeticae, 1801, when he was only in his early 20s, published this monumental treatise in number theory, which really recast the entire subject. He actually had a very good look at these cyclotomic polynomials, exactly of this kind, when p is a prime, and he was able to prove that they were irreducible. But his argument was rather long and not so easy. So it's not an elementary thing to prove. And then a little bit later, Thomas Schoenemann in 1846 gave a result which is basically Eisenstein's criterion, but it became known as Eisenstein's criterion due to the work of G. Eisenstein in 1850, who was actually, I believe, a student of Gauss. Now, although it's usually called Eisenstein's criterion, it's a little bit unfair because Schoenemann deserves, I think, equal credit. And I think in prior times, this was given more equal credit. And we're going to move in that direction. So from now on, we're going to refer to it as the Schoenemann-Eisenstein criterion. Okay. So the first thing that we want to do in our next video is to go into this in a little bit more depth. So this entire question of factorization really depends on us knowing a little bit more about irreducibility in the world of polynumbers. So the equivalent property of being a prime in the number theoretical world. And we want to explain this Schoenemann-Eisenstein criterion, so we'll be able to prove this kind of thing. Because identifying irreducible polynomials or polynumbers is an important part of this story because we want factorizations into irreducibles. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.